Okay, let me start with this slide. This is about the trace element behavior in magnetic systems, right? In magnetic systems means always either melting or crystallization, right? It can be melting, that means mantle melting, or crystallization, not only mantle melting, even crustal melting, right? Magnetic system, wherever the magma is involved in a rock system, right? So we discussed about the compatibility and incompatibility, right? So the compatibility means the partitioning of elements into the solid phase, right? The elements which prefer solid phase we call compatible elements. The elements which prefer the melt or the magma we call incompatible, right? So when the mantle melts, right? Because we mainly discuss about the mantle melting, right? At this stage, we call fertile mantle. That means the mantle which is composed of peridotite lithology, which is able to produce melt out of it, right? Upon heating or upon decreasing pressure, right? Decompression, right? Remember, either heating or decompression can both cause melting of the mantle, right? So mantle convection makes this decompression because the lower the deeper part of the mantle are brought into the shallow levels. That means sudden pressure decrease. So at that time, during this convection process, partial melting of the mantles begins. Okay, it's not the complete melting, partial melting. That means it produces a residue and a melt both, right? So you have a melt produced and the residual portion of the mantle is remaining there as the solid. So since we have now the single phase is evolved into two phases now, solid and liquid, the elements can behave differently because some elements like solid phases while some elements like liquid phases. So now the partitioning can take place, right? So the original set of elements which were available within the mantle region will now get into fractionated or partitioned into two components, right? One is solid, one is the other one is the liquid, right? So this is what we call the partitioning. So preferential moving of elements from one phase to another, that is what we call the partitioning. So the compatible elements goes to the solid phase, or rather it remains in the solid, because the before the melting you have anyway the solid, right? Solid mantle, and after melting you produce some melt here, while you remain the solid again, remaining part of the solid, but that solid actually it's a modified solid, right? Geochemically modified, because it has contributed already a melt component. Therefore, the composition is different from the original state number 1, and this is the state number 2. So this solid is different from the original solid. So the more compatible elements will be concentrated within the residue, while the more incompatible ones concentrates within the liquid phase. So elemental concentration wise, the residual mantle has high concentration compared to its original state in terms of compatible elements, right? The opposite is true for the melt, right? So this is what happens during the mantle melting. Please enter your what the registration numbers in the chat box to mark the attendance. Okay, right. So the incompatible elements we divide further into two groups. We said one group is HFSE, the other one is LFSE, right? High field strength elements and low field strength elements. So high field strength elements are small elements. That means they have the small atomic, the small ionic radius, but the charge is high. That means the valence is high. The charge is high. So this ratio we call the ionic potential, right? Ionic potential is greater than 2, right? Typically. And for low field strength elements, they are large. Their ionic radius is big, but their charge is low, right? So these are called large, low charged cations, whose the ionic potential is less than 2. 2 is the determining factor for these two categories. Above 2 and below 2 are considered as the limit, right? So HFSCs, for example, you can name some typical elements like zirconium, hafnium, niobium, and tantalum, right? So these are the typical high field strength elements. And typical low field strength elements, some examples you can consider: cesium, rubidium, potassium, barium, even strontium, right? These elements. Actually, these are called another name, that is large and lithophile elements, right? Because their ionic radius is anyway large. And anyway they like rocks, right? Lithophile, right? That's why it's called lithophile, because there is a classification: lithophile, siderophile, atmophile, like that classification is also there, right? Anyway, this is called large and lithophile elements also, these low field strength elements, right? And then you have elements with the same charge. Some important feature is there, where the elements with same charge and size, right? So if you have two elements with the same charge, that means same valency, and the ionic radius also, right? So we expect them to show similar geochemical behavior, right? For example, we take some couples of elements like lanthanum, cerium, rubidium, strontium, and also we have similar characteristics shown by some of the high field strength elements, that is zirconium, hafnium, this couple, and niobium, tantalum, these two, right? They also have the same size and same charge, so therefore they exhibit similar geochemical behavior properties, right, during magmatic processes. That means that the partitioning behavior, whether it is during melting or crystallization, showing similar characteristics. So mostly these same size and same valency bearing elements are nearby elements in the periodic table, right? Like lanthanum, cerium, rubidium, strontium, like, right? But in this case, the zirconium, hafnium, niobium, tantalum are not closely lying elements, right? This is a special case, right? So anyway, these similar elements with same charge and size, approximately same charge and size, should show similar geochemical behaviors. So due to that reason, we used to take these two elements together in graphical representations, right? When we want to draw some geochemical diagrams, we prefer to take these elements because they have similar, they should show similar geochemical patterns, so that it reflects in diagrams in both, probably in x-axis and y-axis, if one element is increasing its composition while the other one is also showing the increase. That means like a positive correlation or a negative correlation can be expected by selecting these two elements together. Otherwise, the behavior might be a little bit complicated, so that we might not be able to easily interpret such geochemical behaviors in some unknown samples, right? So that's why we have to select those closely aligned elements for presentation of some diagrams. We'll see those diagrams, how we can use them later on. Okay. So I think you can remember this content we have already completed before, and Now let's see some further details on trace elements and their comparison with the major elements, right? So in the case of major elements, their magnitude, we don't see much big sensitivity in terms of mantle melting compared to that of the trace elements, right? Because the major elements are concentrated in magmatic systems or in rocks or in magma uh, in large amounts, right? You know that already, right? It's more than 1 weight%. The minimum is 1 weight% for their concentrations, right? So if something is less than 1 weight%, we usually don't call them major element. Those might be trace elements or minor elements, right? So if you see this diagram, we call this type of diagrams as Harker diagrams, right? Harker variation diagrams. So you can see some kind of variation there. Let's see how does this change. For example, you can see some trend in these plots, right? First, you have a trend like this, and then you have a trend like that, right? So a trend like this and trend like that in terms of uh, decreasing direction of silica, right? Silica decreasing. Here is the silica component, right? X-axis is represented by silica, y-axis is represented by various major elements, oxide form, because in XRF we get these elemental concentrations in oxide form frequently. So we can use it directly, or otherwise we have to convert it into elemental concentrations by dividing by their molecular percentages and atomic proportions, right? But it's okay, we can represent them in the oxide form. That's more convenient. And here the magnesium shows a variation like this, right? So that means during the decreasing silica content, what happens? The magnesium content is gradually increasing, right? When the silica content is decreasing. What do you mean by the silica content decreasing? What kind of a uh, scenario is there? Decreasing the silica content. Yes.
Crystallizing.
Sorry.
Crystallizing silica.
Crystallizing silica. Yes. That when that means some mineral crystallization. Okay, good. So that means what happens to the system? Most probably this might be a liquid system or a magmatic system. So initial magma silica composition maybe take 70 or 75, and finally it has come to 45-50 level. So that means what has happened? What has happened to the magma composition? What has happened?
When part of the magma crystallizes, the remaining residual part concentration is increased.
Yeah, residual part. Yes, residual magma. The composition changes. What kind of a change you can expect there? How do you interpret that? What kind of a composition? I mean, the original magma is now different, right? That's why we call it residual magma. So what has happened to the residual magma now in terms of the composition? Silica must have crystallized. That means the crystallizing phases must have taken up a lot of silica, making the residual magma into what? So if you have 75% weight percent of silica in the original liquid, in the original magma or melt, means what kind of a magma you have originally at the beginning? What kind of a magma? Composition wise? Yes, highly felsic. Yes, highly felsic magma, right? 75 silica means it's very, very acidic, very high felsic magma. So now what has happened? 45. Let's take it as 45. The 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 composition has decreased. I mean, in terms of silica, that means felsic nature has decreased a lot. So in other words, how can you say that?
That magma converted into mafic.
Yeah, the magma has converted into more mafic composition, right? Through an intermediate composition, right? Maybe intermediate in the middle here, and then it's turning into more mafic composition, right? Not very, very mafic. I mean, not ultra mafic, but mafic anyway, right? 45 is mafic, right? Close to, I mean, 40, 45 means mafic, and 30 to 40 like ultra mafic, right? But it has not gone to that level. But anyway, it has gone to mafic composition, like mid-ocean with basalts composition, right? Mafic composition. But originally, it's like the granitic magma, right? Normal granitic magma, right? So that change has happened to the magma. You can see the compositional change of the major elements. For example, magnesium. Let's take here. Magnesium is almost like 1% at the very beginning, right? Even less than 1%. Now it has become very high, up to 10, right? 10 to 8% of magnesium means highly mafic magma. So the maficness has increased a lot, not in terms of silica, but also in this iron magnesium pairing phases, right? So that means a lot of magnesium rich phases should have been crystallized during this process. Okay. So these type of interpretations are important when you look at the diagrams, right? So that's why we are taking major, not only major, but trace elements as well in magnetic systems for interpretations. But now we are trying to compare trace and major elements to make the representations in terms of their magnitude. Okay, their magnitude shows difference, very difference. So in this case, even though silica composition from 75 to 45 means a very large range, the change is very huge. But still, the magnesium composition has, I mean, in weight percent, if you take 1 to 10% has changed, right? If you take aluminium, probably aluminium is here like 13, 14, 14 or 50, 14% like weight percent. And then that was at the beginning of while the magma was at 75 silica. But now at the middle, maybe like intermediate composition here, the aluminum composition has increased up to like 18, 19, 20, let's say 20, like that. It has become increasingly aluminum rich while the system evolves from high silica to intermediate silica. When it goes to more mafic compositions, aluminum has somehow decreased, right? So it's a special characteristic here. So that means originally it increases and then decreases, right? It's a some specific, I mean, two geochemical processes or two geological processes has happened during this magmatic evolution. So this is an important observation which you don't see much with respect to aluminum magnesium composition, right? Of course, there is some deviation here, right? You can see here, probably the same thing is reflected there as well, but not very sure. But here, the more high resolution can be seen in terms of aluminum composition. We have to think about what kind of a geochemical process may have taken place there. It's another exercise, but for the time being, we don't care that second process. But anyway, you can see the variation, how this variation happens. So when you can see the temperature, the silica content from 75 to 45 change, still you can see only some few weight percent of aluminum has changed. Originally 12, now like 19 or 20, right? So few weight percentage has changed. And for iron, so why you have star here, FeO star? Can anybody tell me why this star there? Any guess why this star is there? You will see frequently this star together with the iron. What can be? No? Because iron is measured as total iron. Okay? What is total iron? You know, iron has two species, mainly ferrous and ferric, right? So this separation is not happening in the XRF. So it gives you all the iron content as a total iron. So that is what is indicated there, right? When you have ferric oxide, then you can specifically denote it. Otherwise, it is normally given as ferrous oxide with star, right, together. Right? That is the indication. So anyway, you can see again the similar variation like magnesium, but even that deviation around here, you don't see here. That means it's not sensitive. Iron is not sensitive for that variation, right? That geochemical process. So if you just look at only even calcium, right, the same way, if you just look at calcium and iron, for example, right, uh, and try to interpret some geochemical process, you can only interpret this increase of calcium or increase of iron with decrease in silica, right? You can't find something you saw here in terms of uh, aluminum composition. That means you saw from aluminum composition two processes, right? But those two processes are hidden in calcium and iron composition. Even magnesium, you don't see it much better resolution, although you can see some deviation here, right? You don't see that in iron, calcium, but for titanium you might see a little bit, right? Here you can see a slight variation, and for potassium you never see that, and phosphorus you can see that variation, right? So that's why we have to take into account multiple elemental data, right? Otherwise some processes are hidden, you can't understand, you can't identify, right? So we call them geochemical traces, right? So this is how we try to trace different processes, hidden processes, because now we have is just the rock only, right? We don't know what has happened in the past. So we are trying to analyze them chemically and try to interpret what has happened in the past, right? For that you need to consider multiple elements. That's why. But anyway, the magnitude wise, you can see the variation is not very much. I mean, iron does not, or iron, aluminum, calcium, magnesium, or anything does not change from 10 to 100 or something like that. Originally 100 and then now 10, like that. No, no such change. Originally 12, now 20, or 5, now 8, or something like that. Few weight percentage change only reflected, right? That is the nature of the major elements, right? So the advantage of studying trace elements is we can see huge variations uh, in trace element behavior, right? So that reflects largely, I mean, the sensitivity is too high, so that any hidden pattern can be discovered, right? But in this case, for example, even iron, calcium, you see only one variation, because the variation is not large enough for other processes to show, right? Only few weight percentages are changed. But in the case of trace elements, or even trace elements, you will see magnified variation, right? Highly magnified variation. I mean, some few ppm, because it's always less than 1%, right? Trace element composition. So mostly it can be like in ppm or ppb also, right? So this variation reflects much in most of the cases, right? For example, 100 ppm may be at the beginning, but finally it might have reduced to 1 ppm, 2 ppm, something like that, right? So this characteristic feature, which has which is possessed by the trace elements, are advantages for us to understand trace element behaviors in igneous systems, right? So the magnitude is very important. The magnitude variation in major elements is comparatively little than what you see in trace elements, right? So you can see here the trace element magnitude variation, right? So we have trace element now, the same silica variation you can see, here. But you see at the beginning, say 75 silica time, the trace element composition is like 250 ppb, but finally it has reduced to 50 ppb or so, right? In this case, nickel at the beginning, it's like almost very close to zero, by few ppm, but now finally it has gone up to 200 ppms, right? So this variation is very large, and more high resolution you can see those two processes. For example, here you see the two processes have happened, probably the same process as was reflected by the major elements here, which was slightly replaced, right? Even if you had little amount, number of samples, you can see these black dots represent the number of analyses, right? Number of analyses. So if you had only few tens of such analyses, then even aluminum will not reflect this curved behavior. But definitely trace elements will show you, even you analyzed less than 100, little amount of little number of analyses. Okay, so zirconium does not show such variation anyway, because it may have a different behavior in that system. So although they have shown a large variation, you don't see this particular pattern reflected by nickel here, right? So zirconium might not be sensitive for that particular process. That is also a possible reason. Okay. So anyway, the importance of studying trace elements is this. Okay. The magnitude wise, the elemental change is highly emphasized there in igneous processes. Okay. So any question up to now? Do you have any question? Okay, now let's see the element distribution, because in all these igneous processes, elemental distribution from one phase to another depends on some special features or properties that these trace elements displaying. So therefore, we have to check those elemental distribution, whether they are consistent with some kind of a law, right? In according to a rule or a law, right? We call it the Goldsmith's rules, because the Goldsmith was the one who categorized the periodic table into different geochemical groups, right? So that was done by Goldsmith. So he categorized, and even he categorized the elements into atmophile, siderophile, lithophile, like that, right? That classification is also from Goldsmith. He is the father of geochemistry, we consider as. Okay. So the first rule of Goldsmith is two ions with the same valence and radius, right? So that means almost identical ions, two ions with the same valence and the same radius should exchange easily and enter a solid in amounts equal to their overall proportions. So what does it mean? They should exchange easily and enter a solid in amounts. For example, in melting, you have a residual solid, right? Residual solid. So for the residual solid, some elements enter, that means compatible elements, whereas for the liquid, incompatible elements enter, right? So in the solid side, if you consider the solid side, the entering element amounts in amount wise equal to their overall proportions. So that means whatever the proportion you had in the prototype, in the original source, should be equal to the residual solid also, right? So the proportion of such elements, if you had similar type of elements, I mean in terms of valency and the radius, right? So if you had say A and B elements, two elements in 1:2 proportion, right? So in the residual solid also, you must have the same those two elements in the same proportion, right? It doesn't mean the same concentration, right? Remember that proportion only. If you take the ratio composition or the compositional ratio, you will have the same proportion there, right? That is the first rule of the Goldsmith, right? And there is another rule. That is a second rule. It is said that if two ions have different radiant, the same valence, right? So now we should have the same valence, right? Same valence, but different radii. The small ion is preferentially incorporated into the solid over the liquid, right? So this, irrespective of their compatibility or incompatibility, the incorporation into the solid phase, because I mean any element can incorporate, right? It doesn't mean that having compatible and incompatible groups in elements doesn't allow to partition into both phases, right? Even compatible elements partition into liquid phase, right? To some extent, right? It doesn't mean that they don't get any compatible element, right? They get, but the more they get is incompatible for the liquid, and the more gone to the solid is compatible, right? Right, but even for the solid, you have incompatible elements, right? It doesn't mean that they cannot accommodate there, right? It's not like that, right? So they, irrespective of that feature, that incompatibility or compatibility, so if you have any smaller ion, I mean two ions with same valency but different sizes, the small ion is preferentially incorporated into the solid. So in that case, the small ion is preferentially partitioned into the solid phase compared its partitioning into the liquid phase. So that is the second rule of Goldsmith. These rules indicate the behavior about explain the behavior about the phases. I mean behavior about the elements in phases, right? Solid or liquid phases, right? Now you can see one diagram here, right? You have a diagram, so we'll take it later in description. So this diagram shows Just a minute. This diagram shows this is what you call a phase diagram, right? So phase diagram, this shows Forsterite composition, right? Forsterite composition, that is iron and magnesium content in olivine, right? Forsterite and phthalate, right? Those two, one end member is phthalate, the other main member is forsterite, right? And with the temperature, you have the y-axis as the temperature, because that is the crystallization of olivine from a liquid, right, is different at different temperatures. I mean, the amounts is different, right? So during this crystallization, the iron and magnesium ratios, this is magnesium and iron ratios, are also different in the system, right? So if you take this region, in this region you have both liquid and olivine. That means both solid and liquid is there, right? Two phases are there. So in this type of a situation, definitely you have two phases, right? Liquid and solid, right? So liquid and solid you have there. So Goldsmith rule applies for a system like that, right? Not a single phase. So here, if the elements are there to partition into the two phases, because when we change the temperature, elemental behavior changes, right? So so the elemental partitioning can be changed from the liquid when you increase the temperature, for example, right? That is what you call the diffusion, remember, right? So that can happen. So smaller iron, when you have a small iron out of two ions that have same valency, the smaller one will go into olivine, right? The small ion will go into olivine, and in the liquid phase, you will get the more bigger one there, right? Irrespective of the compatibility or incompatibility, right? So that is the second law of Goldsmith. In the first case, two ions with the same valence and radius should exchange easily, and they enter a solid in the amount equal to their overall proportion. So originally, the proportion should be same in the case of the same size and same valence ions. But if you have a same valence but smaller in size, then that smaller one will preferentially go into the solid phase. That means when olivine is crystallizing from this liquid, olivine will contain a lot of small ions compared to the bigger ones which is available there, although they have the same valences, right? So that is important to characterize the elemental partitioning or preferential partitioning of elements. That is according to the rule 2 of Goldsmith, right? Their partitioning. Okay. So this is okay. I think you better have a sketch of this phase diagram with this rule 2. Please just have it. Okay, right. So there is another rule, that is number 3. Just a minute. That's rule number 3. If two ions have similar radius, that means same size, okay, but different valence, right? If they have different valence, the ion with higher charge is preferentially incorporated into the solid, right? So in this case, higher charge cation is important because it is more preferred to partition into the solid. So in this situation again, if you have the same size two ions, the higher charged one will go into the solid, right? So in that case, when the olivine crystallizes from the liquid, that is a solid phase, so the higher charged one will go into olivine. So in the case of same valence, what happened? The small ion, that means lower ionic radius bearing element goes to the solid. But in the case of same size, similar size ions, the higher charged ion will go into the solid phase. Okay, so higher charged one will go to the solid over the liquid. So this is how the Goldsmith has identified the behaviors of trace elements in magmatic systems, right? This is not related with any major elements. Major elements do not behave like that. This is only related with the trace elements, remember. Okay, right. So that is how we describe the behavior. And now let's see about the chemical fractionation, where when we have several phases, 2 or more phases, we call it competing phases. Competing phases. Why do we call competing phases? There are several phases which prefer to take up some trace elements, right? Yeah, there may be not only 2, more than that. Everybody wants to take up trace elements, right? They have the potential to take up. That's what we call competing phases. So this competeness, how much they can compete to each other, depends on their individual properties, right? So anyway, because of that, there is always uneven distribution between phases, right? Because each phase has its own limitations. So therefore, the distribution is uneven. For example, if you even consider these 3 rules, you can understand whenever there are competing phases, the atomic size, valency, all matters for their partitioning. Okay, right. So when the exchange we consider, when you have a component I, for example, an element I, for example, in the liquid phase and the solid phase, right? So the exchange equilibrium of component I between 2 phases should be explained in an equation like that, right? So actually this is related with the ratio of their relative compositions, right? The composition of an element in the liquid phase and its composition in the solid phase. At the equilibrium state, if the solution is in equilibrium, that means no phase within that system reacts with each other, right? So you may have several components within the magma, but nothing reacts with each other, right? That is what you call the equilibrium. Otherwise, if reactions are taking place, it is not an equilibrium system. So the behavior is very complicated. You can't, the Goldsmith rule is violated there as long as they are not in equilibrium, right? It should be in equilibrium status. In reactive status, we can't interpret anything unless you wait until the system becomes into a equilibrium situation. Okay, right. So this ratio, for example, you can take this as I liquid, or I, let's take solid, because most of the geochemical equations, they are solid is at the I mean, we have to take as a ratio from solid to liquid, like, right? So I liquid, you can, if it is in equilibrium state, you can put it as equal sign, and you can even put this as a constant, right? Because on the equilibrium state there is no reaction, so that means this ratio should be constant, right? Nothing will change, nothing will cause for changes in the system, right? So this K, this K is called the equilibrium constant, right? Equilibrium constant. So you can define it in terms of activity in the normal case in geochemistry and even chemistry. You take it as the activity, not just the concentration, but still you can use the concentration as well, but it's more better represented when you take it as the activity. Okay, activity of the element I in the solid phase divided by activity of the element I in the liquid phase. That is constant while the system is in the equilibrium status. Also, you can represent this using the activity coefficient, something called activity coefficient, because concentration itself might not reflect this behavior for all the elements. For some elements, you can just represent this by the concentration ratios, but it might not be correct, right? It depends. So you have to take the activity coefficient here for that particular element, multiply it by the concentration, right? If you take the concentration values, right? That ratio will also be constant and equal to the equilibrium constant, right? So this is regarding the exchange of equilibrium of a component I between these two phases, right? If you take two phases, right? Then if you further consider this one, right? If you further consider this one, okay, let's take it here. You just remove this K from this equation. What will happen? Activity, you have activity in the solid, right? Of for a particular element, which is directly proportional to activity of that element I in the liquid phase. Okay, so this is directly proportional, right? So you can interpret it like this also. If you remove the equilibrium constant, right? Because it's a constant, that you can remove a constant from an equation and make it in the proportion terms, right? So actually this is what we call the activity varies with the concentration. So this is again an interpretation for the Henry's law, right? So this is what you call the Henry's law actually. That means for a given element, its activity is proportional to its concentration, right? This is what we call the Henry's law, and the trace element concentrations or behavior in magnetic systems is according to this Henry's law, Henry's law pattern. Okay, so we call this equation as the Henry's law equation, also due to that reason, right? So in a competing system, as long as they are in equilibrium phases are there, the trace elements will behave according to the Henry's law, right? Henry's law states concentration of an element of a system at a given condition is proportional to its concentration in the liquid phase, right? The two phases, solid and liquid, their activities are proportional to each other. That is what you can consider as the Henry's law. So in simple terms, if you want to make it in simple terms, right? If that means because you can have a system here, right? This is a complete system. There may be many phases, right? You can have olivine, CPX, OPX, like that. Many phases can be there, but you have one fix. The concentration for the whole system also, right? You can take, for example, you can take nickel composition of this system as some say 10 ppm, right? 10 ppm. Okay, you take it as 10 ppm, and each phase here, nickel, olivine, OPX, CPX, spinel, or whatever. These different phases might also have nickel incorporated into their structure, but their composition may be different, different numbers, right? Concentrations, right? 2, 3, or 4, something like that, right? We don't know that until you analyze it. The whole rock system contains 10 nickel ppm. So according to the Henry's law behavior, if you make this system in equilibrium conditions, so each and every phase activity should be directly proportional to its concentration, right? According to the Henry's law for a given trace element, right? So if you take nickel as a trace element and its concentration in the system as X nickel, if you make it double due to some process, if you make it double, that means you make this 10 into 20 somehow during this magmatic evolution of the system, maybe magma mixing or further melting or remelting or whatever. Another process can make original concentration into double, right? So that means it's according to this Henry's law behavior, because the directly proportional behavior is explained by the Henry's law. The system doubles its composition. The nickel composition in each phase should also double. Otherwise, it is not directly proportional, right? So for the system, if it becomes double, for each phase also it should be double. So it doesn't mean that for each phase you will have 20, right? For the system it is 20, it is doubled already. So for the each phase you must have doubled the composition. That these 2 must be 4, these 3 must be 6, okay, like that. Each phase will have its composition double, because from the system only they can get nickel into their on phases, right? For each phases, what you get from the system. So if the system doubles, what you get will also be doubled, right? Because of this Henry's law behavior. So this is what is explained by the Henry's law, right? So this is the whole rock compound. Always remember this 20 doesn't come by 3 plus 2 plus 1 plus something like that. No, it's not like that, because it all depends on the model percentage, its partition coefficient and everything, right? That makes the whole system 20, right? It doesn't make by just simple addition of the concentrations in each phases. No, it is not like that, right? Because these are represented by volumes, right? So this is a different thing, right? When you make chemical solutions, right, you know how to make the concentrations. Okay, right. So anyway, the point that I described is not meant that nickel in all phases will be the same, right? No, it is not like that. It's just doubles whatever they had initially, right? So because you know the trace elements do fractionate, they fractionate, right? So that's why you can't expect the nickel to behave similarly in all the phases. Nickel behaves differently in different phases because you have different partition coefficients for different elements for each phase. So therefore, uh, that is another thing, right? So, but it doubles anyway if the system doubles, right? So that's why it happens like that, right? No, always you cannot expect everything is coming equally unless you have same valency, same atomic or the ionic radii, then you can expect similar distribution, right? So I think I gave you one example, one assignment. In that assignment also you had one question, one part of a question to think about this. Although I did not uh, teach by that time, it makes you to think uh, about the partitioning behavior, because already we discussed partitioning behavior and partitioning coefficients, etc., right? So you may have just considered that fact when you answered that one, right? I haven't corrected them yet. So I will look into that, and we can discuss it in the class later on. Okay, right. So, uh, so within each phases, the proportion will change, right, according to the system concentration. So that is what Henry's law explains, right? So this is a very important thing when you consider this mantle melting and crystallization processes. That means magmatic systems, right? So previously we discussed about the incompatible elements. So that means whatever the preference is there for elements to the melt are incompatible. So by the definition of this trace element, this equilibrium constant, we always take, we are used to take the solid in the solid over liquid, right? This relationship. So therefore, if you take an incompatible element, what happens? For the liquid, you have more incompatible elements, right? For the liquid, you have more incompatible elements compared to the solid, right? So that is our definition. Incompatible elements uh, must be highly concentrated within the liquid than the solid. So what will happen for the equilibrium constant if you take the incompatibles, if you take according to that definition, right? You can make it upside down, but traditionally we make it in that way, right? So always remember KD or D, sometimes it is represented as D, should be less than 1. It is less than 1 uh, because you have it a higher concentration in the in this ratio here, right? So this numerator and denominator matter, right? So this is, please give me a minute. Okay, right. Did you get that point? For an incompatible element, if you write the equation, always the KD should come less than 1, right? For a compatible element, it should be always above 1, because we have solid over liquid, the concentration, right? So that's why. Okay. Sometimes you can make this KD as D, and also directly taken as the concentration, right? I said sometimes it is taken as concentration, but if you take the concentrations, actually you have to take the activity coefficient as well, right? This is the activity coefficient, right? This is the concentration, right? But very dilute solutions, if you have dilute solutions, because in magma you have trace elements in ppm, right? In ppm means parts per million, so that means it's not weight percent, right? If it is weight percent, then it's high concentration, right? But still it is ppm or ppb sometimes, so that means it's very dilute solution, right? We can take magma as a dilute solution for a for some elements, right? Majorly for all trace elements, you can take it as a dilute solution. So therefore people used to denote it directly as the concentration ratio as well, right? So that's why we have to consider it as a dilute solution. So you just substitute kd into t there as the distribution coefficient, right? So equilibrium coefficient or constant can be termed as distribution coefficient in a dilute solution, right? So since the trace elements in magmas are in ppm levels, because they are low concentration, that's why actually we call it trace elements, right? Then you can take it as directly concentration ratios, right? No harm, even you don't take the activity coefficient there, right? Okay. But if you can calculate the activity and take the activity ratio as here, that is more precise even, right? So that's okay. Right. So the concentration in the solid phase is denoted as Cs divided by Cl. So that tradition doesn't break there. You have always solid over liquid relationship. Okay. Right. So any question up to now? Do you have any question? Is there any question? Okay. Right. So we can still consider further details for incompatible elements, because in geochemistry we have to take into different groups, right? So remember high field strength elements and low fields, large and lithophile elements. Yeah, low field strength elements, large and lithophile elements. We already noted in a previous slide, remember, about the categorization of these elements, right? These incompatible elements subdivided into HFSC and LFSC, right? Remember? So this is again, I'm mentioning here because for the high field strength element, previously I did not show you, the typical high field strength elements that I showed you are zirconium, hafnium, niobium, tantalum, right? We take these high field strength elements here, you can see zirconium, niobium, these two, and hafnium, tantalum, right? These elements are high field strength elements, but not only those, actually you can take even the rare earth elements, right? Even these rare earth elements, that means lanthanide series ones, also as the high field strength elements. So if you make a complete list for high field strength elements, then you will have to take the trace elements, the rare earth elements as well, right? You can put the rare earth elements plus thorium, uranium, lead, right? also into this category, right? Cerium is already included there, right? With the rare earth elements, right? Here, cerium and lanthanum, right? It should come here, okay? Lanthanides, okay. So remember the all these high field strength elements can include the rare earth elements also, right? Not only this zirconium, niobium, tantalum, plus titanium also. Actually, titanium we don't take always, because in some rocks, titanium is considered as a major element, because TiO2 comes in weight percentages in some rocks, especially mafic rocks, because when you have rutile like faces, right? Rutile mineral, titanium is very high there. So it makes titanium in the rock into high proportion, high concentration. So therefore, uh, it goes away from the trace element definition, right? It comes greater than 1 weight percent. So in that case, you can eliminate titanium, but in some situations, you can take it as a trace element also, right? But anyway, its behavior is similar to high field strength element. So therefore, irrespective of its concentration, it can be taken into the HFSC group. Okay. So the large and lithophile elements, we discussed rubidium, cesium, barium, strontium like elements. You can put the potassium also there, right? And europium also, right? Europium 2 plus, remember, europium 2 plus. Usually europium 3 plus is included in the rare earth elements. Do you remember? Europium 3 plus should be there, right? Europium is here anyway, but europium has speciations, 2 plus, 3 plus, and even 6 plus, right? So 2 plus is considered as large and lithophile element, whereas 3 plus is considered as high field strength element, right? It's different. Okay, the charge is different anyway. You understand that for the definition, low field strength and high field strength, the charge matters. Okay, right. So if you take it, if you consider it in a diagram, ionic charge versus ionic radius, ionic charge versus ionic radius. You can just consider high field strength elements which plot here, right? That means they have high charge around this way, but small size, right? For the low field strength elements, they are large, their radius is high, but charge is low, right? So this is how it comes into the variation diagram, right? So 2 ionic potential, we define ionic potential as the ionic radius divided by ionic charge. When the number becomes 2 here, right, this line represents the low field strength elements and high field strength elements, 2 categorizations, right? High field strength elements and low field strength elements. Okay, anyway, these are incompatible elements, so more preference is there for liquid phases, right? Okay. So these properties are very important. Therefore, you have to always keep in mind about their properties. I mean, the relative differences. They are very important, because as I said before, we use these trace element behaviors as geochemical traces. Geochemical traces means some characteristic features for geochemical processes, magmatic processes, right? So that's why we use the term traces. Traces means like indicators, okay? Geochemical traces. So we can find out different processes, whether it is a mid-ocean ridge setting process, or ocean island setting, or plume related, or rifting related, or subduction related, like that, right? Especially subduction related, these high field strength elements variations are very characteristic, very important. So we'll see them also later on how they are used in interpretation, in geochemical interpretations. Okay, right. Okay, we discussed about the compatibility and incompatibility because always this comes into the picture, right? So whenever you talk about magmatic process, uh, compatibility or incompatibility matters a lot, right? Even crystallization or melting, both, right? So we can define partition coefficients, right? So remember, partition coefficients are defined as concentration in the solid divided by concentration in the liquid, right? So it's same as the distribution coefficient here. You see the distribution coefficient or partition coefficient, you can take both as together, because as long as we take the dilute solutions. Okay, right. So if you want to find out partition coefficients for each element listed here, right? So in this case, the melt composition is also important, because not for all melt compositions these partition coefficients behave similarly, right? It's different even for same elements and same phase. The partition coefficients vary, considering uh, the melt composition, right? So basaltic and andesitic rocks, uh, you can take this table as partition coefficients. You can see olivine 0 0.01, 0 0.01, 0 0.01, nickel 14. It's very large, right? Nickel. So that indicates nickel has high compatibility to olivine, right? If you have a high partition coefficient, means that particular element prefers a lot. I mean, they have a big preference to that phase, right? So whenever a crystallization happens, uh, almost all the nickel available in the system can be concentrated within the olivine, right? So that is happening. If the melting happens, most of nickel will remain in the residual portion, because nickel will like to retain in the olivine, because melting, when melting takes place, initially at the beginning, uh, pyroxenes will tend to melt, right, before olivine. Olivine goes at the last stages, right? Whenever that happens, anyway, a lot of nickel which was available even within other phases, even if pyroxene had nickel contained in it, while melting, that will go into the residual nickel phases. Okay, right. So chromium also has a little bit larger value, 0.7, compared to other elements like rubidium, which have 0.1. I mean 100 times lower, right? The second decimal point here. Okay, for the rare earth elements, you can see still very low partition coefficients are there. But when it goes to the heavy rare earth elements, it slightly increases, right? 0 becomes 0.1, 0.2, 0.4, something like that, right? When it goes to the heavy rare earth elements. But light rare earth elements are very low values, you can see in olivine. OPX also contains very low values, almost similar behavior, but you can see comparatively, nickel has low value compared to olivine, but chromium, see, has a high value. Right? OPX can take more chromium than olivine. That means, right? Again, here light rare earth elements and heavy rare earth elements are showing higher preference for heavy rare earth elements for all the pyroxenes, but much bigger in preference than olivine. Right? So this is the comparative behavior of elements uh, in different phases, right? So if you take the CPX, you can see these large and lithophile elements are not much concentrated there. Nickel a little bit higher than OPX, but still lower than olivine. But chromium you can see much higher than anything else, right? So that means CPX can take a lot of chromium. Chromium can be very high in CPX, and you can see the rare earth elements, but you can see the middle rare earth elements are also a little bit higher in CPX, and heavy rare earth elements again goes a little bit high compared to the previous two phases. And garnet, you can see chromium and nickel, but not very large. It's lower than OPX and CPX. And rare earth elements, if you take heavy rare earth elements, have a characteristic high preference to garnet. See, big numbers, 6, 4, like that, larger numbers compared to pyroxenes and olivines. Right? So in a peridotite mantle, depending on these phases, you can guess how their elemental composition would be, right? Of course, the model percentage also matters. How much each and every phase is there is also important in determining their compositions. So at shallow mantle levels, you have the plagioclase, right? So you can see the plagioclase can have a high preference for strontium. Okay, plagioclase has a high preference to strontium, and you can see the europium also relatively high preference is there in plagioclase, up to 1.5, right? So it depends, different valencies, 2 plus and 3 plus. 3 plus has this 1.5, right? And the ratio you can see the different ratios. And the heavy rare earth elements are not much gone into the plagioclase structure anyway. Right. This stroke doesn't mean ratio, okay? It's just 0. Oh, okay. 2 plus has the high preference, isn't it? Yeah. 2 plus has the high preference. Sorry. Yeah, we will see the behavior of europium in plagioclase in magmatic systems. So I will just give you some indication characteristically for plagioclase, because you see the plagioclase does not have large variations in partition coefficients except for europium, right? Except for europium, because europium has a high I mean a big difference, right, compared to the other ones, maybe more than 10 times or 100 times different than the other ones. So it is represented characteristically. So when you plot europium with other trace elements in a diagram, so we have to look into these diagrams later on. Europium, you will see if plagioclase has gone from the system, this shows a very large depletion like this. Okay, europium will be very much depleted if plagioclase has crystallized from the system. That means if plagioclase has crystallized as a phenocryst, that will carry a lot of europium while crystallization. So that means in the system, in the residual system, you will see a depletion of europium, right? So if you have dissolution of plagioclase, plagioclase, so you will see an opposite behavior like this, positive peak, right? So we call them positive anomaly and negative anomaly. These are very characteristic because you can see all the other trace elements have relatively low values, numbers of the partition coefficients, unlike the other phases, because the other phases, although high and low ends are there, still you can see some moderate values, right? Here, some moderate values are there. And therefore, this type of characteristic depletion or enrichment you can't see in other phases. So this europium thing comes as a very characteristic feature for plagioclase because of that. Okay. So we will discuss about trace element patterns in different diagrams in different rocks using different diagrams. Okay. Right. So if you take the amphibole, because these are the most common phases that we encounter in mantle rocks, so that's why they are listed here. You can see amphibole, right? Low values, high values are there for nickel, and relatively larger value is there for chromium. And middle rare earth elements, you have a relatively large values, bigger values, and also for heavy rare earth, heavy rare earth elements. So anyway, from middle to heavy rare earth elements, you can see some preference for amphibole. Okay, compared to very low, very light rare earth elements like lanthanum, cerium. Even those have a little bit higher values compared to previous phases. So that means overall, all the rare earth elements like to partition into amphibole. It means this is also almost one, isn't it? Right? But yeah, almost all the elements, almost all the trace elements have some preference not some, comparatively better preference, to amphibole compared to other phases, because you see even Garnet 0.04 or 0.01, something like that. So that's low, right? But amphibole has 0.2, 0.4, like that, right? Even for rubidium strontium, like large and lithophile elements. So that means irrespective of their categorization, whether it is low field strength elements or high field strength elements, amphibole can accommodate anything, right? That should be the conclusion. Amphibole can accommodate almost everything. So if you have an amphibole rich rock, you can expect high concentration of all the overall elements, trace elements in that rock. Okay, right. So we have an opaque phase, also magnetite, which is not very important for us anyway, but just for comparison, you can see with olivine, it's 29 for nickel, right? So that means nickel can go much high quantities to opaque phases, right? Particularly magnetite, right? Even better than olivine. Chromium also can go in large quantities to there. And you can see other trace elements, right? Even rare earth elements, everything has a big preference to partition. So that means magnetite is a good sink for trace elements, right? Although we have some kind of negligence towards hunting magnetite for trace elements extraction, right? But the thing is, why it is not very much considered? Because magnetite, it's an accessory phase which is occurring at low model percentages compared to these silicate minerals. That's why, right? But if you are going for accessory phases like zircon, monazite, magnetite, hematite, these phases, accessory phases, then magnetite is a good choice for trace element extraction. Okay. Right. So this is about some partition coefficients for basaltic and andesitic rocks. For granitic rocks, the partitioning behavior is different. Partition coefficients will be different. So this is the partition coefficient that we considered were for minerals, right? For each phases. But if you take a rock as a whole, then you have to consider everything there. That means you have olivine, you have OPX, you have CPX, everything is there in different proportions. These elements will partition into that according to this table. But if you want to define a partition coefficient for a for an entire rock, then you have to consider each and every phase with their model percentages. Okay, with their model percentages you have to consider, otherwise you can't take. Right? So in that case, this partition coefficients becomes bulk distribution coefficients, right? So you remember partition coefficient, you can call it just distribution coefficient also. So then they are termed as bulk distribution coefficient or bulk partition coefficient, you can call it, right? So that also counts the model percentage also, right? So this is the weight percentage or model percentage of that particular mineral in that rock, right? So if you have mineral A, then you have to take that model percentage, and then you have to take the distribution coefficient or partition coefficient of that particular element that you are interested in for that particular given mineral, right? So for example, if you take olivine, so you have to take olivine, the partition coefficient of element I in olivine and the model percentage of olivine, right? So multiply this and you add. So the sigma mark indicates addition, right? So everything. So you have second phase, you have third phase, you have fourth phase, maybe OPX or CPX, amphibole, anything. So you calculate this and take as the bulk distribution coefficient. So this is how we define the partition coefficient or distribution coefficient for a entire rock, right? So this is also very important. Okay, so right, so this is about the distribution. And remember the Henry's law behavior, the activity is proportional to the concentrations. Sorry, the partitioning is directly proportional, right? This is directly proportional, right? So I have again the table, and you have a calculation, example calculation for this particular element. Yeah, so you have the hypothetical, we'll take garnet lacerite. So this is a mantle rock, right, which contains garnet. So that means we have considered relatively deeper mantle portion, right, because garnet is present not in shallow levels. Okay, about 100 kilometers like depth, you can expect garnet in the mantle. So lacerite is normal mantle anyway, but garnet lacerite means deeper mantle, right? If you had spinel lacerite, it's moderate, and plagioclase lacerite, it's shallow, right? In the mantle, different depth levels. So in this case, the garnet lacerite, that means a deeper mantle, but not the lower mantle anyway, right? In the upper mantle, but deeper parts, deeper sections. You may have 60% of olivine, 25% of OPX, 10% of CPX, and 5% of garnet, right? All by weight percentages given. Normally, the maximum weight percentage of garnet is around 5, right? It doesn't, rarely it can go up to 8 or 10, right? But usually not greater than 10 anyway, because it's very hard to have very, very garnet enriched mantle in the earth, right? That is the natural observation. You may have 10% of garnet to the maximum, right, in a garnet lacerite. If too much of garnet is there are some very exceptional places like Norway. You have a huge amount of garnet in the mantle reported in some xenoliths, right? So these garnets and these mantle are not really lacerite. Actually, those are garnetitites. Sometimes it's defined as garnetitites, the rock name, okay? Because it is rich in garnet, right? Mantle garnetitites, sometimes it's called, rather than calling it a lacerite. Okay, right. So if you want to calculate the whole the bulk distribution coefficient for garnet lacerite here, you have to consider all these model percentages and respective partition coefficients. So for example, You can take olivine 60%. So you have the modal percentage here, 0.6, and multiply it in the what do you call the partition coefficient for this element in olivine. So let's see, 0.026 multiplied by modal percentage, right? So the addition, the total addition will give you the bulk distribution coefficient of for that particular element for the given rock. This is how it's calculated. Okay, right. So this is how we take all these things into consideration during mantle melting and crystallizations. Okay, do you have any question? Do you have any question regarding this content? Okay, right. So we discussed for olivine, for example, the nickel, the partition coefficient is relatively larger, right, compared to other elements, right? So if you want to see a variation of nickel partitioning into olivine, so with the reducing composition of silica, that means when it becomes more and more mafic, right, you will see a deviation of nickel composition like this, right? You can see a deflection there around here. Deflection is there. So this indicates some special process, some special process has taken place there where a lot of olivine has crystallized. Okay, a lot of olivine has crystallized. Actually, this is happening because you know you have in the mantle CPX, OPX, plagioclase, spinel, OPX, plagioclase, spinel, and olivine, right? So I said when this sorry, this is olivine. When this melting or crystallization, melting takes place, first to melt is CPX, then OPX, then can be plagioclase, spinel like things start melting. Finally, it becomes olivine, right? When it comes to olivine coming into the solution after melting a lot, there will be huge amount of nickel coming up, right? Because olivine contains a large amount of nickel. So that deflection comes over here because originally when melting these things, you don't get much nickel there, right? But as soon as olivine also comes into the liquid, right, after melting, partial melting, then a lot of olivine, a lot of nickel will come into the solution. I mean the residual composition. So therefore, normal variation becomes a sudden deflection like this, right? So before that level, you see the nickel concentration is like 50 around here, okay? But all of a sudden it increases and it has gone up to 200 even, right? Like that. So this is how variation of trace elements when they are brought into liquid after melting, right? So this is an important geochemical behavior. So all these what is reflected here is the variation of partition coefficients, right? So variation of partition coefficient in different melts. Okay, so this is about the melting in the mantle and how the partition coefficients reflect different processes, and also how we can divide different elements into categories depending on their properties. So these are the facts that we have discussed so far today. regarding these different igneous processes, right? So always remember these magmatic processes or igneous processes refer not only melting but also crystallization as well, right? Okay, so do you have any questions? So this is the significance of trace elements, because compared to the major elements, as we stated before, their reflection, their sensitivity is high because they contain a little amount only, right? When you have a very little amount, then only you reflect when it lost, right? If you have few people in the class and if you lose one or two there, the effect you can easily recognize, right? But when you have hundreds of people in the class, when you lose one or two there, you never recognize it, right? So that's the difference between major elements and trace elements. So that's why igneous petrology people and geochemistry, geochemistry people are very much interested in trace elements than major elements, right? Because their changes are very, very sensitive and reflective enough to interpret different geodynamic processes. Okay, so I think with this content, we can stop here for today. So if you have any question, you can ask now. No questions? Okay, so then we'll stop here for today, this lesson.